Hello community! Today we look inside the brain of an AI transformer architecture and we have a look at the geometry of sorts. So, welcome to my channel Discover AI and we have a look at the latest AI research papers. Now the question today is when and where does the AI transformer model internally decide what solution path to take? And now we have a new research which is absolutely amazing. Let's have a look. We have the Department of Linguistics from Stanford University, Physics of Intelligence Group, NTT, Center of Brain Science, Harvard University, and the Department of Psychology from Harvard University, because they look at it more from a brain scientific brainwave kind of view. So this is a framing that is interesting. It is not our normal computer science view, but I think they find out something absolutely fascinating, multidisciplinary research. You know that we have our LLMs, our autoregressive systems that provide step-by-step answers. They have a next token prediction, and we only see a single path that the LLM took. But at every word, it could have gone a different way. It could have found a different solution. Instead of yes, maybe it was no. So let's have a closer look. Can we know when it is really confident, our AI, versus, hey, when it was just guessing? And how can we see that the roads not taken by the AI, or can we see the probability of some certain decisions? Let's say it was a 49 to 51%. How can we make sure that we have here a real solid ground decision by an AI machine? Now, simple. Let's do a test and generate some thousand futures as predicted by the AI system, and then we just evaluate it. So let's do this. So what we're building is, if you want, a confidence meter for an LLM. So first we create a lightweight uncertainty monitor. So we will build here a very simple linear probe based on AI, and this will explore our LLM's hidden state to act as a dashboard. This is a computational cheap method to flag when a model's reasoning is on shaky ground. Let's say its own confidence vote is below 30%. Even when the output token probabilities seem high, because we want to dive into the internal thought process of an AI mind. Now, you are familiar with these forking paths in neural text generations. If you remember December 2024, Harvard University, NTT Research University of Chicago, Department of Computer Science, and they did a beautiful golden rule, and they established here the forking path. What is it? To generate a wave path, you just give a prompt to generate a single complete chain of thought response generated by the AI X star. And then you identify some forks. So this means that each token position, and I really mean that each token position in X star, consider not just the token that was chosen next, but also the set of n highly probable alternative tokens W. So let's say for each token there were 10, 20, 50 alternative tokens that the AI could have chosen, but did not. And now we explore those paths. So for each alternative token W at the position T, create a new prefix followed by W. From this fork prefix, generate S complete sequences. 10, 20, 50, 100. Complete reasoning path that define complete different prediction by the AI, that define complete different futures. And then you aggregate the outcomes, extract the final answer for every single generated sequence, and you have several thousands of them, and you compute the weighted average, and this gives you the outcome distribution O at the time T. It's simple, no? But it is extreme computational expensive to do. So let's take a simple example, and I want to show you here this on a basic example. The correct answer here is, if you do the multiplication first, but a common mistake, and a lot of AI even today do here the addition first, so there is now a difference between the result 20 or to be 30. And let's think the AI is a little AI and it makes a mistake. The AI says, hey, let's think step by step. First we do the addition, no? We go here in a linear sequence. 10 plus 5 is 15, multiplied by 2, we get 30, so the answer is 30. Now we as human, we know this is the incorrect answer, but let's use this now to have a look what other futures would have been possible. The first step is to isolate the forking point. When did it go wrong? So we look at the moment the model chooses the word, hey, I want to add this, and the model did not choose the first mathematical operation is multiplication is first. So the text that was written by our autoregressive large language model so far was, okay, let's think step by step. First you do the, and now comes the interesting part. Because if you look now here in the layer, in the activation patterns of the transformer itself, and you extract here this, you see that the token addition with a particular code has a 70% probability. And this is the path that it took. But there's also a second place multiplication that has also a non-neglectable probability of 25%. And we know that this is a real important alternative path that maybe the AI should have taken. And then we have some, just 2% probability, just a synonym. So you see, this is exactly what we want to find out. So what we do now, we force the model down a new path. So we take the alternative correct word multiplication, and in this forking of the paths now, we force, quotation mark, the model to use it. So we have a new starting sequence that becomes now, hey, let's think step by step. First you do the multiplication. And then the AI runs again with next token prediction. So you see, you generate a new future, a new prediction by the AI. So we give this new sentence back to the model and ask it to complete the sort, and you will see, okay, now we have the correct answer, 20. And you do this for every single word in the sentence. And if our original sentence here with let's think step by step and whatever has 23 words, in the simplest case, if we only generate 200 futures for each word, we go here not really deep into the logical chain. This means we generate 4,600 futures, and the authors did this because they wanted to find out, is there a certain reflection point when suddenly, let's say, half of those 4,600 futures converge to 1 or 2. So let's have a look at this. Now, just imagine we would have a little bit more complex mathematical thing, but no, we stick just here to the simplest mathematical operation we can think of. No? So what do we do? How do we get here? At the word let's, the very first word here of the sentence here, the model is not sure. Exploring futures from here might show a 50-50 split between the answers 20 and 30. No? It's too early to have a decision. But at the word, as I showed you, addition, so at place number 7, this is the key moment. And the model shows now at once that we say the model decides on addition, virtually 100% of all the other futures and with the answer 30. So you see, this is our inflection point. And if we force the fork to the second most probable word, like multiplication, it shows that 100% of the futures would have ended with 20. So you see, this at position 7, with either addition or multiplication, this choice of a token decides the complete future of the prediction of the AI model. Now, you know, even for a simple question, this is incredibly expensive. But it gives us a perfect high-definition map of the model's certainty. And it allows us now to say with confidence, hey, the model went wrong at the 7th word, at the 7th token to be, if you have a token word identity, when it chooses addition over multiplication. This was the point of no return. So looking now at the activation patterns, you have now, I guess, what we're going to do. We are going to find out where the reasoning in an AI is going to happen. Welcome to the prime paper of today. This is here, as already showed you, Harvard University, linguistic and whatever. Are language model aware of the road not taken, of this B probability? Token level uncertainty and hidden state dynamics. And this is here November 6, 2025. And they consider exactly this. What are the alternative paths? And now I think this is interesting because if you could read out this path, you understand, hey, if your AI gives you an incorrect answer, you might ask, is it because the AI could not find that there is the correct answer? Or was the correct answer just at second position, but for some interpretation of some conditions, the AI decided just to rank it here at the second position? Or was the AI unable, because the complexity is too high, to find the correct solution at all, and not in the top 100 prediction of this AI model is the correct prediction. So you see, if we know this, we have here a real flashlight looking into the black box of even proprietary AI systems. So what do we have? So for every single token in our example, now we have now a pair of things. Now, of course, if you do it professional, we read out the activation pattern from an open source model. So this is, if you want, a snapshot of a model's internal brain activity. And you see, Harvard, this here is psychology. This is not pure computer science. So, but interesting to see this from a different point of framing. Yeah? So the internal brain activity of the AI, the transformer layers, at the exact moment, this is just a vector. No? This is no problem. Let's say, I don't know, 125 dimension or whatever. And then we have the true outcome. No, of course. We have the answer 30 with 55% and the answer 20 with 45% and so on. And we can do this for every single token. So this means we have to build here this, if you want, forking of the path and the activation patterns, the readout. And then we have something, guess what? This is now our training data set for our new AI predictor machine. Let's call it a translator, no? And you know what? It is a linear probe. And the only task of this linear machine is, hey, given the activation patterns of our AI model, predict now the true outcome. So what we do, we show it an activation pattern, and in the training process of this translator AI machine, this machine makes a guess. So we show now the true outcome from our answer key and tell it how wrong it was. And the probe then adjusts its internal math slightly to become better next time. And we repeat this 1,000 and 1,000 and 10,000 of time. And we trained our AI translator machine. Great. And I know what you want to say. You say this is too simple. You have a linear probe of a complex cross multi-self-head attention transformer architecture? Are you joking? Let's have a look at it. So we go back to the problem. Hey, 10 plus 5 times 2. Model starts by writing all that things step by step. First, you know this, no? But please don't forget, you are doing this on a multi-layer transformer architecture. So we have to read out all the layers, no? So let's say we stop at the word do, no? And we don't generate any new futures. We just reach now into the model's brain, this predictor AI machine. Say we go to layer 12 of the transformer and grab the current activation pattern. Where is this model? Where's the decision process of this AI machine? And then we feed this pattern vector, this current activation pattern vector, into our new trained translator AI machine, the linear probe. And then the translator, since it was trained on this pattern recognition and pattern prediction exercise, the translator instantly split out here a prediction. Like the answer 30 will be 55% and the answer 20 will be 45%. So what we have done, we have taken an extreme complex transformer machine. We build now a simple linear probing AI machine to be trained here on the activation pattern and the probability distribution. And we hope that this translator AI machine will do the job for us so we don't have to generate 4,600 futures for each and every sentence. So therefore, we have to do it once in order to be able to train the translator machine. And then when we grab here the new activation pattern, if we have now the token addition, and feed it to our translator, we don't have to calculate another 1,000 of futures. It instantly spits out the new prediction, 30 with 98% certainty. So you see, nice. But this is not what is really interesting of this study. Because remember, it's a prediction. So we are predicting the entire distribution of all future outcomes of this transformer directly from the model's current internal state of mind, the activation pattern of each specific layer, maybe the higher layers here in the transformer architecture. And now you might say, but wait a minute, this learning is really limited to this particular case, to this simple task, to this simple transformer architecture, where we already had to calculate thousands of futures to be able to learn here a linear probe AI machine. And now we extrapolate and interpolate those data for our new cases. Should this work? And I ask myself the question, hey, is it that linear that we can do this brute force prediction with a linear probe? Now, the surprising answer that the authors give us is yes. And now this is now the most interesting part of the study. So there a lot of work went into the first part, but now to understand why this is possible is absolutely fascinating. And if I talk about linearity, you understand we are in a high-dimensional vector space, and linearity is not simple here, a light beam like this one or this one or this one, but we do have here a certain space-time structure of the normed vector space itself, and. So the mathematical complexity is not as simple, and I hope to show you this here, limitation here with this image of mine. And I think this is one of the most shocking and useful discoveries here in the interpretation of an AI thinking process. And it turns out that for many core concepts, and please read the study by Harvard, it's really interesting, the model's internal brain space, as the psychology department of Harvard called this, is linear. And you know what? This goes beautiful with this video, I think it's about a week old, where I showed you from another perspective, from a pure computer science perspective, that this geometric memory was discovered here in AI machines. And this is now an additional supporting fact. It is not a mathematical proof. It is just a further hint, if you want. Yes, we are back here to geometric memory configuration. So this means when a model is trained, it learns to organize the information efficiently. And the easiest way to store your two opposing concepts, even simple as multiplication or addition, is to put them on opposite side of a simple flat dividing line, and let's call this a hyperplane. And the linear probes, AI machines' only job is to find here the angle, that is the dividing line between those. And once it finds it for a math problem in general, of this complexity, on this domain, with this LLM, it can then apply it to any new math problem of the same complexity, because the new problem activation patterns will also fall on one side of that line or on the other side. So we do achieve now kind of a new generalization. Plus, and now hold on to your socks, to the emergent geometric pattern. I call it's a return to geometry, interestingly, but on a much grander and a more profound scale. And we thought, hey, this is just a black box. We have no chance of ever understanding the internal thought process of an AI with billions of nonlinear operations that we could not map. And now, with this study, there is a way to do this. And if you look at the activation space, and if you analyze it, like the authors did in the study, you see that the internal world, or let's call it the activation space from the computer science framing point of view, behaves according to geometric rules. This is a simplification that is simply beautiful. So single concepts like truthfulness or sentiment, or here like the uncertainty about a final answer, doesn't live in a multidimensional intertangled knot structure with highly dependencies. It manifests itself as a simple direction just in a high-dimensional space. I mean, it couldn't be easier. We have a linearity. I'm interested. I'm really interested where we can go with these ideas. You know that some of the concepts that I already showed you in my other videos can be grouped together. And all the activation corresponding to correct reasoning might cluster now in a region of the space, while the incorrect reasoning clusters in another. And if those regions are, and this is now a hypothesis, are linearly separable, so simply meaning you can draw a simple flat plane, a hyperplane between them, then our job would really be much more easier here. But remember, there is this kind of paradox, no? how does here the complexity of the transformer architecture with all the different layers and multi-head self-attention and or whatever you have with cross-attention, how does it create suddenly in this thinking process, let's do this here, these human terms on a machine, how does it create this simplicity geometric patterns? Because I expected it to be a highly interwoven, high-dimensional mathematical metric or a tensor structure that is just crazy to look at. And now we have geometric patterns. And I think this is here kind of an open question. Huh? How is it possible to have here in an energy optimization problem here that you find maybe a local minimum or a global minimum here on a certain manifold? How does it happen that those solutions in those minima are of a geometric shape? I find this absolutely fascinating. So kind of now again, hypothesis only. We are entering an era where interpreting LLMs is becoming form of a digital geometry. The more we understand of the internal geometric patterns that the AI is using in its thought process, the more the internal thought process open up for us human to understand. So we're not just looking at output probabilities anymore, or logic or whatever. No, we are mapping now the fundamental geometric structures of the model's internal thought process of our AI machines. And I think in this regard, this particular study is also really interesting. And this is why I wanted to show it to you. But of course, it also means if I understand for a particular AI model, let's say a llama model, since it's such an old model, and understand exactly where the model reasoning path has its weakest point, where there is, if you know this, where the model has not decided yet to go with the word add or multiply. If I go there and I can identify this particular neuron, or if you want here in the transformer architecture, this in particular network knot, and I just add a simple vector, I can move here the complete reasoning of the complete AI machine in complete different directions. And maybe, and this is here the red path here, with some intention that were not intended here by the original programmer. So this opens up massive security problems, because if we would understand for a particular model, a particular machine, exactly where just to add a vector. I mean, this is, you can, how to formulate this? You can convince the model that, hey, there's a vector waiting for you. No? You don't have to code some crazy whatever. It becomes then just going after the internal logic that the AI will change its complete future prediction process. All future decisions by this AI will now converge on a complete new endpoint that somebody could define. Absolutely fascinating study. Have a look at it. Read it in detail. Would be interested to see your comments. In any way, I hope to see you in my next video.